Hi everyone, my name is Ashwin Raghuraman. I'm a Senior Solutions Architect at AWS.
Hi, I'm Brian Miller. I'm a Senior Principal Engineer at Riot.
And I'm David Press, also a Senior Principal Engineer. I work across League of Legends and TFT.
So for those of you who aren't familiar with Riot Games, they're a AAA game studio who publishes free-to-play games. They're based out of California, and they produce games like League of Legends, Valorant, Wild Rift, Teamfight Tactics, Legends of Runeterra, and 2xKO soon to come. They don't just produce games, though. They've also built the world's largest esports circuit with hundreds of players, hundreds of teams, thousands of players. But they've also built their brands to transcend sports, media, entertainment, and fashion. In 2022, Riot Games and AWS partnered together, and we've really accomplished a lot. We've built things like the first global power rankings for esports, a best-in-class remote broadcast center powered by AWS, the very first machine learning-powered esports statistic, and even migrated all of Riot's data centers into AWS. But all of this stuff is in the past, so if you're interested, please check out aws.amazon.com/sports/riot. But for the talk today, we're going to really take a look at how Riot was able to make use of AWS EC2 autoscaling to reduce their infrastructure cost for their games. On top of that, we're going to deep dive into Riot's game provisioning platform and really understand how they make the best player experience. So take it away, David.
Thanks.
Oh, wait, you don't need this.
I need the clicker. Yeah, there we go. All right, thank you. So just to set a little bit of context, League of Legends is now over a 15-year-old game. It's a player versus player team-based game where you're on a team with 4 other friends and you're playing a champion, one of about 160 champions we have now. Each champion has a unique set of abilities and spells that it can sling at your opponents. Your opponents can dodge it. At the end of the match, you're trying to basically destroy the other team's base. And it's a very fast-paced game. There's a lot of back and forth and a lot of action that can happen over the course of the game. We also publish a game called Teamfight Tactics. This is more of a strategy game. It's a little bit slower paced. You get a little time to think about how you place your champions, and then they kind of play on their own. You're not really playing on a team. You're playing by yourself against 7 other players. Each round, you're trying to defeat one other player, and then the last person standing is the winner. So to power this, both League of Legends and Teamfight Tactics, we have an architecture that's at the highest level divided into platform servers on one side. These are kind of your standard web service stack, Java services that deliver the out-of-game experience. So this is like your login, your store, matchmaking, the progression systems, battle passes, that kind of stuff. The client communicates with these services generally over REST, HTTP, kind of very standard stuff. On the other side, we have game servers. So this is what powers that in-game experience where you're casting the spells, or in TFT, you're placing your characters and they're fighting each other. This is a much higher latency sensitive experience. You're sending lots of UDP packets, these small packets that really need to get to the game server and then to the other players as quickly as possible. So as I said, League of Legends has been around for quite a while now, over 15 years. And as such, it was kind of born before the cloud. And so to power these, especially the game servers, which needed to be close to players, we had to build out a very large on-premise metal data centers around the world. And so it was not just in North America or Europe. We also had to put it in more far-flung locations like South America, Southeast Asia, Turkey. And so this was a big challenge for us. It was also one of our competitive advantages that we were able to go so wide around the world and serve all these traditionally underserved players who were really big fans of League of Legends, and it really allowed us to become that global esport because we were able to serve all these players. Game servers have a lot of specialized needs. They're not just the low latency, but they're also a very computationally expensive process. It needs to power kind of a soft real-time simulation. In general, we try to keep the game servers running each frame of simulation at around 30 frames a second. And so it's really important that they are that they get the CPU time to run that fast. On the other hand, we're trying to pack as many games onto a server as possible so we can be cost efficient. There's a lot of this communication that goes between the game server and the clients. These small UDP packets that I talked about, they really need to get to the game server as quickly as possible so it can process them, advance the simulation, and then show the results of what that player did to the other players so that they have a chance to then, say, dodge that spell that you just cast. Another unique thing about game servers that makes them different from a traditional web service is each one needs to be individually addressable. So with a typical web service, you're behind a load balancer. It doesn't really matter which web server a certain request goes to. One request from a player might go to one web server, and then the next request from even the same player might go to a different one. Doesn't really matter. However, with game servers, that game simulation is hosted on a single server, and so players need to be able to reach that server. And so that means each game server might need to be publicly addressable by clients, and that actually exposes us to denial of service attacks very easily. If a player is malicious and they're say losing a game, they can direct a bunch of traffic at that server that they're playing on and take out the game server, and then the match isn't recorded, and they can do a little bit better, advancing their rank that season. And then at the end of the match, we need to get a ton of data about what happened in that match to all of our downstreams kind of progression systems. So it's not just win or loss, it's also all the things that happened in that match. You might have achieved a bunch of challenges, like I killed 5 champions of this type, and so all that data needs to get shipped out of the game server and to those out-of-game experiences. So this is kind of the architecture that powered our game servers for a very long time. On the left-hand side, we have the client. Down kind of the middle horizontal, we have the path of like starting a game. On the right, we have an EC2 instance that is one of maybe thousands of game servers. And each one of those is hosting a number of games. These EC2 instances, or in the case before we were on AWS, it was just servers. These were all Windows servers. We first developed League of Legends game servers on Windows. It was kind of a natural fit because our client also mostly runs on Windows, and all of our developers are very comfortable with that. And so we started off on Windows, and we had a very large fleet of these Windows servers running. On the bottom is kind of the end-of-game flow. When a game finishes, it sends all the end-of-game data to an end-of-game data service, and then all the downstream services kind of consume that data and present some of it back to the client. On the top, we have the connection from the client to the game server itself. It goes through a DDoS appliance, which helps protect our game servers. So there are a number of pain points with this architecture. The first one, being on-premise, was just scaling. So we were constantly growing the game, especially in the early phases. We were launching new features that required new capacity, and to do that in a sane way, we had to be very conservative. We had to purchase a lot of extra capacity to make sure that we had enough in case our forecasts weren't perfect. And so this led to significant waste, significant cost, but we had to do that to kind of do the right thing by our players. So obviously, big opportunity to be able to take advantage of auto-scaling. Another pain point was that DDoS appliance that I mentioned. We contracted a popular network vendor to build us a custom FPGA-based DDoS protection solution, and that it worked pretty well, but it had a number of limitations. One of the main limitations was it could only support 255 games per host, which starting out, that was fine, but as servers got more and more powerful and you could shove more and more cores inside of a single server, that became a big limiting factor for us. Another constraint that this solution posed was it could only support up to 2 versions of the game running at once. That was a problem once we launched TFT as a mobile product. With mobile games, you're not always able to send a patch through the App Store and get it approved at a certain time. And so you end up having many versions of the game running at once, and that became a big problem with our edge solution that could only support 2 at a time. And then I mentioned that we were running Windows game servers. One of the problems with that is just the licensing. There's a cost there, but also an overhead for managing all those licenses, running audits every once in a while, making sure that we use those licenses properly. Another element of using Windows licenses on AWS is if you're bringing your own licenses, which we were, you have to use EC2 dedicated instances, which impose an amount of extra overhead as well for how you provision those and how you manage those. And so that was extra complexity on top. And then Windows system administration is just, at least at Riot, is becoming a bit of a lost art. We were focusing all of our training and investment in managing an even larger fleet of Linux servers, and we just weren't getting any much better at managing all the intricacies of running a large Windows fleet in production. And so that was becoming a bigger problem as we kind of lost a lot of that expertise. And so fast forward to 2020, and we launched a new game called Valorant. It was a first-person shooter game. It had a very hard infrastructure requirement. It was even required even lower latency than League of Legends. We were targeting 35 milliseconds to all these players, and we kind of used Valorant to learn a lot of lessons from the pain points that I just mentioned with League of Legends. And so Valorant was really a cloud-first infrastructure launch. We launched across 12 AWS regions, 4 AWS outposts, and then 5 Riot data centers where we still needed a presence. We also used 2 different edge networks, our own Riot Direct edge network, as well as AWS Global Accelerator, to really get those packets from the game servers to the players as quickly as possible. And so this actually was a really successful launch. Valorant was running on Linux game servers, running on containers in the cloud. This allowed us to take advantage of auto-scaling, and it was great. We learned a lot of lessons from League of Legends, and we had a very successful launch of Valorant. But that made League of Legends a little sad. We're still running on Metal. We still have all these pain points, and we're looking at Valorant and saying, hey, why can't we have that? What's it going to take? And we did a little bit of analysis. Oh, this is quite a lot of work. We still need to make a whole game and keep iterating on it, and we wanted some help. And so that's where we turned to our player platform team at Riot, and that's where Brian will take over.
All right, so to kind of set the stage of where we were when League reached out to us, you kind of got to understand what problems we solve. So player platform is a kind of common central team. We solve a lot of the generic problems that games have. So, so you'll have, So you'll have a lot of the services that are listed right here are, you'll have a lot of the services that are listed right here are, you'll have a lot of the services that are listed right here are 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 services that solutions that we provide to multiple games. So this is the common stuff. You'll have accounts, you'll have social, we have the behavior systems, but we had started looking at creating solutions in the game space itself. So it was originally intended to be something for 2XKO, which is our upcoming fighting game. They had asked us to go kind of riff off of Valorant solution and create a cloud-based game provisioner that could be used for their game and multiple games. So we were kind of busy working on that. And so we had come up with a design that was kind of loosely based on the best practices that we had come up with, which is, of course, scalable and fault tolerance, which is something that every game provisioner needs. Worldwide support, and because Valorant game servers run on Linux, that was one of the things that was needed in order to ensure that we could scale effectively, because many of the other games run on Unreal, and Unreal runs, or at least the Unreal that distribution that we're using was running on Linux. So at this point in time, a post-GDD league approached us and asked us to possibly pivot, and instead of solving problems for 2XKO, take this and move over and provide a solution for League itself. So we did, but in order to do something like that, we needed to kind of modify Valve's architecture a bit, because it is incredibly effective for what they're doing, but they have made some choices that were very, very specific to the game itself. So they did have the generic packet watermarking David was talking about with UDP traffic, ensuring that we have an anti-DDoS solution, but it wasn't as generalized as we wanted, and it wasn't something that was going to be plugged into League's ecosystem as effectively as we wanted. There was a need for native patcher support, and this is actually really cool. We've baked our game server patcher distribution model into GPP itself to provide that multi-version support, so that when a game team pushes their client assets out, their game server also becomes available, and the version parity can be leveraged, so that when you play the game and you download it, it can connect to the right version of that game server. So we can support multiple game server versions at the same time. And we really wanted to have a built-in, very solved problem in end-of-game processing, especially since it's critical to how we understand the end of game and the game results that come out. We want to make sure that everybody still gets their battle passes. So another obligatory architecture slide. This one is somewhat similar to League's. There are some small differences, though. We decided to have 4 central kind of scheduling locations. So a game team's platform just has to worry about one of 4 locations to start games. And we have many pods, and within them, many pod instances that run an agent to manage the game lifecycle. So this really simplifies how a game platform interacts with starting and managing game server instances. All right. It also allows for an immense amount of expandability, because game teams just have to worry about sending games to the scheduler. If there's a new pod that they want to target, as long as the resources are available, we can go start games there. So in order to kind of kick this particular initiative off, which was now kind of a pivot away from 2XKO, we assembled additional people, because moving League is quite a bit more than trying to set up things for a game that we're looking to launch. So we pulled resources from League. We had a large number of individuals from our central infrastructure teams, as well as a lot of support from our awesome AWS representatives. And we were looking to roll out across all the places that League currently operates, which is, of course, their testing environments, their live environment, esports, and all of the partner regions. But it was not all smooth sailing, and David will talk about that.
Yeah, so there are a lot of challenges moving League onto this new GPP platform. As Brian mentioned, Valorant solved things in a certain way that worked well for Valorant, but not everything, the situation wasn't the same for League. It was an already launched game, and we had a lot of work to do to kind of migrate the ship while it's in flight. So the first challenge was we had all these game servers running on data centers, and we needed to migrate them to AWS. So we kind of did that as a first step. There was a whole talk we did actually at reInvent last year that went over this project. We call it the Global Data Center Decommission Project, which took several years and kind of migrated us from what it was here around 2014 to where we are now, which is in even more locations around the world, and now we're a mix of AWS regions, local zones, and outposts. And we actually migrated our final live data center last month in Istanbul, Turkey, to an AWS outpost there, and so we are now fully on AWS and cloud for all of our game servers. So the second challenge was migrating our game server from Windows to Linux. And so when you're working on a code base for 15 years and you're on a certain platform, you make a lot of assumptions about being on that platform. So you're using certain OS-specific APIs, and so you have to port all of those. You have to just kind of get it to even compile, and then you have to start testing it. And so we had to do a lot of performance testing. Because the game server is such a performance-sensitive application, we needed to make sure that it at least matched our Windows performance. And so we did a lot of testing kind of locally and then in our testing environments. And we actually used our public beta environment to squeeze as many games onto a single host as possible and kind of determine where it breaks. Does it break it around the same time that it did on Windows? And we were actually surprised with how little performance tuning we had to do to basically match the performance of Windows on Linux. We also ran into a lot of platform-specific bugs. You start relying on a lot of undefined C++ behavior that works in a certain deterministic way on Windows, but then when you run it on Linux, it's a little bit different. So we actually had a case where we were using a certain standard library container, which was a unordered container, but on Windows, it kind of had a deterministic order that we were relying on with one of our game scripts. And when we moved it to Linux, it was a different deterministic order still, but it basically caused certain players were playing one of our pirate champions, Gangplank, and there's a certain ability combo that you could do. You're dropping a bunch of barrels and then shooting them at the same time. And we found out actually after we were live that players in the regions that had been migrated to Linux couldn't pull this off anymore, but the ones on Windows regions that we hadn't migrated yet were still working. And so I was like, oh, this is definitely something OS specific. We narrowed it down to this container bug, and then we switched to a different container that had the same behavior. And all that led to basically a packet arriving and being processed one frame later, which meant you couldn't pull off the combo anymore. So very sensitive to those conditions. And then the final challenge that we're really going to deep dive into is how do we leverage autoscaling for these game servers? So when you set up autoscaling for a typical web service, the first thing you need to figure out is what's kind of the CPU threshold at which your customers start experiencing problems. And so this might be like the latency of your request gets too high, or transaction processing takes too long. And so in the case of game servers, it's actually when the frame rate of the game server dips consistently below 30 frames per second. That's when players start feeling the game being unresponsive, your champion is hitching, and it's just a bad player experience. And so first you got to figure out that kind of what we call the player pain threshold. And empirically, we kind of determined for League of Legends and TFT, that's around 80% CPU. So the next thing you got to figure out is what's the threshold of CPU at which you'll start scaling up. And so this has to be below that kind of pain threshold, because you want to give the autoscaler enough time to recognize that that you're above that threshold, and then it takes some time to spin up a new instance and then start taking the load off the other instances. And so you need to put it below that threshold. And so the question is, how far below? And so one of the things that plays into how far below is what is the variance around your average. And so when you have a very high variance, like I'm showing here, you need to move that threshold lower, because that means that when you have a certain host that's varying high above the average, it'll get close to that player pain threshold, which you don't want to exceed. So here's kind of a visualization of two graphs, one where you have the high variance and one with the lower variance. With the lower variance, you're able to raise that threshold to be closer to your pain threshold without actually having anyone reach that player pain threshold. So this turns into real money. If you take a CPU auto-scaling threshold of 40% as your baseline, increasing that just to 45% will save you 11% of your costs. Up to 60% will save you a third of your costs. So it turns into very real money. For game servers, they're the biggest cost in our whole infrastructure fleet, and so being able to save a third there turns into real money. So making sure we could get this as high as possible was very important to us. So the issue was League and TFT have very variable performance over the course of the game, and this is different from Valorant. In a Valorant match, the kind of stuff that's happening on the server is pretty consistent over the course of the match. You're kind of doing the same thing over the first round of a Valorant match as the last round. Whereas with League and TFT, it's very variable. And so here's actually some graphs that show both on the left-hand side, you have the game duration distribution. So a League of Legends game is kind of the modal game is around 24, 26 minutes long. TFT games are a bit longer. And then there's, on League, a pretty long tail of longer games. And then on the right-hand side, it shows the CPU cost over the course of a match. So as the duration of the match goes towards the end, you can see in League, it starts off really cheap, then goes up towards the middle, stays a bit consistent during the middle, and then towards the end of the game, gets a lot more expensive. And so when you think about how a game progresses, your champions start out with only one or two abilities, and the cooldowns, how fast they can cast those abilities, is pretty high. As the game progresses, they gain more abilities, and they can cast those abilities faster. Also, the game kind of encourages you to have these big team fights towards the end of the game where a lot of stuff is going on at the same time. And so that's what leads to this kind of behavior across League games. And it's a bit different with TFT. It also starts off pretty cheap. It gets more and more expensive as the game progresses, as you get more champions that you can place on the board. But then it actually goes down towards the end of the game. And that's because players are dropping out as the game progresses until there are only 2 players left. So there's less going on there. And so it's a bit of a different behavior that we had to contend with. And both of these are different than Valorant, which was just very consistent over the course of a match. So let's kind of zoom in to a single host and see what it looks like when we start adding games to a host. You might have 4 games on a host, so you're running at 15%. You add some more, you keep adding more, it goes up. And then as you get closer to that 80% threshold, you're kind of full now, you don't want to add any more games. But really, as I mentioned, as at least League of Legends games get more expensive over the course of a game, so you can't really fill in that many. You might have fewer games where some are these cheap early games and some are more expensive later games. And so because of this distribution, you can't fit as many of like average games as you can as early games. So we had this challenge of figuring out how do we decide if we have a fleet of game servers, which game server do we pick to put a new game on? And so this is kind of a load balancing problem. And we started with the naive approach of load balancing, which is like pick the lowest loaded game server and put the new game on that one. So let's kind of see what happens there. So say you have a fleet of game servers, they're kind of equally loaded, and the minimum CPU of like one of the hosts is at 70%. So it's below that 80% threshold. If you have a new game, you're going to put it on that one game server that's at 70%. But let's say you add a new host to this fleet. Now your minimum is that new host at 0%. So you're going to put games on that host. So let's zoom in and see what happens. We have this host at 0%. We add 4 games. It's a 10%. So it's still the least loaded one. Let's add some more games. Let's add some more games. We keep going until we get to that 70%, which was the minimum before we added this host. And so now we can start using the other hosts. And it's more evenly balanced. But until then, we kept shoving all the new games onto this host. The problem is these were all early games. We kind of added them all at the same time. And so as these games get more expensive, we start hitting our player pain threshold and even exceeding it as they all get towards the end. So that's a problem. We don't want this to happen. And then all these games kind of got added at around the same time. So that means they're all going to finish at the same time. And so they all kind of finish. We're back to 0%. And now the same thing happens again. So this is what you're going to see, this very high variance around an average, which makes it so we have to put our threshold very far below that 80%. So what we want is a much tighter oscillation. We need a better placement algorithm. The least loaded is not going to work for us. So we kind of went on this quest to find a better placement algorithm. And kind of our design constraints that we wanted to look at when finding one, we wanted to make sure it always kept every host below that kind of 80% threshold. We want it to be pretty flexible. We want it to work for both League of Legends, which works a certain way, as well as TFT, which is a little bit different. We also needed it to work for our different regions. We even see different kind of performance variance between our regions. Maybe players in Korea are playing their champions a little bit different than players in the US. And we didn't want to pick an algorithm that works best for Korea and then another one that works best for EU. And then obviously we wanted it to be cost optimal. That was kind of the point of this, is we wanted to be able to bring that CPU auto-scaling target up. So in order to do this, instead of just trying out a million things on live and seeing what worked, we built a simulation. And so we actually took a bunch of real-world data from our live shards of basically all games that started on a host over a 24-hour period. And we kind of looked at the CPU utilization of each one of those games as it progressed over the course of that game. And then we built a simulation that allowed us to replay all those games, but with different algorithms of where to place those. And so when we ran it with the least loaded algorithm, this is what it looked like, which is about what you would expect. The super high variance going from 0% to 100% and back down, really not what we want. And so, but this kind of verified what the theoretical approach for least loaded would lead us to believe. So simulations seem good. So we came up with a ton of different algorithms. These are all different kind of load balancing algorithms you could think of, round robin, various variations on round robin, just pick a random one, pick 2 random ones and pick the one with the lowest CPU. There's just lots of different variations that we tried out. And then we ran those through the simulation, got a ton of results based on just how those algorithms performed against our data, and how much did they keep the CPU of each individual host below that 80% threshold. Then we kind of created a short list of algorithms that worked for both League and TFT. And we got a bit of a different list for those two because they have different behavior. But going back to one of our design goals, we wanted to pick one algorithm that could apply to both. And when we kind of looked at this list, round robin seemed to be worked pretty well for League, worked pretty well for TFT, and pretty simple to implement. So we kind of went with that. So this is kind of one of our live shards, our EUS shard, and it showed us transitioning from using the random algorithm, which we went live with. You can see the very wide variation around an average. And then when we rolled out round robin, much tighter variation. It's still around the same average, that 50%, but now we can start raising that average, and we can start raising that threshold without hitting that 80% number that we don't want to get to. And so this is kind of showing us actually raising that threshold over the course of about 2 months, and each one of those step ups meant saving that amount of money that we showed in one of the previous slides. And so all in all, we did this migration of League of Legends from our Metal infrastructure over to AWS and GPP, and added Autoscaling. And this is kind of a graph showing our costs before that migration, during the migration, and then once that migration completes. It kind of is steady before the migration. You actually see a spike during the migration because we're actually running both things at the same time. But then after the migration completes, we end up at a state that's almost half the cost of what it was previously. And this ultimately led to basically a savings of as much as 10 million yearly due to using autoscaling and being able to increase that threshold over time. This is one of the single biggest cost savings initiatives we've had at Riot, so big success. So what does this mean for players? We're not just trying to save money, we also want to do the right thing for players. And so this whole project wasn't just about that. One of the great things that using autoscaling and GPP enabled was it allowed us to handle different performance profiles. And so this summer, we launched a new game mode for League of Legends called Swarm. This was a player versus environment game mode where you're one of 4 players cooperating together and playing against these hordes of monsters that progressively get more and more powerful over the course of the game. And this had a very different performance profile from League. One of the things is you have much fewer players in a game. And so there were only up to 4 players, but on average, like 1 or 2. And so even though each game was a little bit cheaper than a normal League of Legends game, because we had much fewer players in that game, we had to have a lot more capacity to support Swarm. And so this was a temporary mode. We kind of wanted to do it as a treat for our players. It was a very different experience. And we were able to support that using autoscaling because we could quickly scale up for that mode. And then when it was done, we could scale it back down. We didn't really have to think too hard about how much capacity are we going to need, because we needed to order all that ahead of time and make sure we had enough. We could kind of rely on auto-scaling to handle that for us. This is something that we really couldn't have ever entertained when we were on Metal. There's no way we would have bought 3x our server fleet just for a 2-month thing. And so this is kind of the experiences we can now unlock because we have a lot more flexibility in our infrastructure. And then we actually followed up Swarm with a new TFT game mode, which had its own new performance profile. It was actually more memory bound than CPU bound. And so we switched from C-class instances to M-class instances for this one. And again, enabled by the cloud. If we were on Metal, we would, it's not like I guess we could have bought new memory sticks and shoved those in everything, but this was as easy as switching your instance type and pressing go, and just being able to support all these different performance profiles gives us a lot more room for experimentation. And so we're going to have Brian kind of wrap us up with some of the further business benefits as well as our next steps.
Man, I love Swarm. That was such an amazing mode. I played so much of it. And then the fact that the thing that we wrote helped make that possible just made it so sweet.
Yep.
Anyway, so we've now got a really awesome cloud-based game provisioning platform that our games can use. So it's like, what does that mean for the rest of Riot? Well, there's some just amazing conversations that have started happening with some of our R&D games where previously it would be a lot of infrastructure, where are we going to go put servers, how are we going to go do, figure out what our footprint looks like. Now the conversations are, what is our latency SLAs, where are the target markets we want to have our game available in, and it lets our games focus more in the areas that we really want them to be focused on. At the end of the day, this should be a commodity. You should just put your game server where your players are and make sure that you're satisfying their needs and they get the best possible experience. And so the fact that we're able to transition that conversation into that particular areas, it's just amazing. It also unlocks some really cool possibilities around latency-based matchmaking. We do have a matchmaking solution, and GPP does ship with a ping implementation, so which is something that Valorant also does. So we can put players that have similar ping in geographically optimal game server locations, so our player experience can be maintained or improved. So you've sat here for a while and listening to David talk about some really amazing stuff and probably wondering what exactly would be the takeaway that we would want. So game provisioning is a complex problem. There's a lot of complex problems. We even started with Valorant that had a viable problem, solution to this particular problem. And as we lifted all of League's ecosystem out and we took our existing learnings and kind of jumbled them together to figure out how to create this optimal solution, we ran into some issues. Some of our baseline assumptions were wrong. And there's this predisposition around when you have something of value and you move it, it's still inherently valuable. And that is that sunk cost fallacy of just continuing to invest in a thing that maybe you should have reevaluated. So part of this is as you move things into different ecosystems, you should be reevaluating your expectations and creating ways to experiment and evaluate and understand if you are meeting your expectations correctly and not just assume that, hey, worked in bare metal, League's been amazing. League's game servers have set the standard for this stuff for years. If we just pop this over into AWS, it's just going to be awesome, good to go, no problems. Let's. So just really making sure that you are understanding those impacts and having a strategy of evaluating and evolving them as needed. And of course, we have this awesome game platform. What are we going to do with it? With any of the upcoming stuff? So it was ripped off from Valorant, but we still haven't convinced Valorant to come use it. I think it's one of those situations where what they have is actually pretty solid. What we have is also pretty solid, but then there's no value in them transitioning off. So improving GPP to provide really compelling features for Valorant to want to move and do that shift is something that we're definitely working on. The Riot Thunderdome, which is a hackathon that we do, was really, really interesting this year. We had 30 game. We always have like game prototypes that everybody does. It's one of the awesome parts of working at a gaming company. But half of those were using GPP for their multi-game, and they were able to do that out of the box. We had hooked that into our Unreal offering, and they had infrastructure that had been set aside, and there were a bunch of games that just were doing matchmaking and gameplay as part of their development. It was really, really powerful. And another really awesome kind of outcome from Thunderdome is that we had one enterprising engineer on GPP that decided that he really wanted to see if he could get League to run on Graviton. So he assembled a couple of other individuals, and they were actually able to set up a game pod with very low cost and validate that that is something that could actually be done, which was pretty awesome. And as I said, our R&D titles are running on GPP now, all of them, including the MMO, and the MMO has a bunch of fascinating challenges that we're going to have to go figure out as we look to support a non-match-based, more evergreen game server model. So there's a lot of exciting things to be done there. And that is all that we've got. Thank you so much for coming and joining us.
Yeah, thank you.